My name is Jung Lee. I present about Relevance-CAM, which is one of the explainable AI method. This is brief summary of our paper. Relevance-CAM is a novel class activation mapping method and robust to the shader gradient problem and able to explain every layer of a model correctly. Figure 1 is visualization of various CAM-based method along layer depths. As the layer goes shallower, the attention maps become noisy except for Relevance-CAM. When using previous method, it may be judged that the intermediate layers cannot extract class semantic information, since the generated j maps cannot localize the class object. But it's misjudging. With result of Relevance-CAM, Resonate 50 model can extract class-specific information even in intermediate layers. This slide is for motivation. Figure 2 shows pipeline of GradCAM. GradCAM authors use the gradient of the target layer as weighting components for each activation map. But the gradient of deep neural net suffers from the shader gradient problem. The deeper the network, the more the gradient is shattered. This is called a shader gradient problem. Therefore, we think that the gradient is not optimal choice as the weighting components for CAM-based method. In that way, we consider using LLP as the weighting components, because in many research it is experimented that LLP is not sensitive to the gradient shader problem and LLP shows more continuous heat map than gradient map. The meaning of sensitivity or gradient is which pixel change is important to increase or decrease output values. On the other hand, LLP asks about how much did the pixel contribute to the model output. In my opinion, CAM method should explain what happened to the model rather what will happen with some changes. Therefore, we choose to use LLP as weighting component. Left figure is pipeline of Relevance-CAM. The overall process is same to other CAM-based method except for calculating the weighting component. We did 5 experiments to analyze the feature of Relevance-CAM. In this video, I will present about 3 of them. First experiment is depth-wise visualization. The figures show comparison of various methods. The columns for each method and rows are divided along the layer depth. As you can see, in shallow layer, layer 2, the result of each method is quite noisy except for Relevance-CAM. Relevance-CAM localize the target class well even from the intermediate layers. This indicates that the shallow layers also can extract class-specific information. Next experiment is evaluation for selectivity. We visualize the weighting components to show how the shader gradient problem damages the localization ability of GradCAM. In figure 5, A and B shows the weighting components for each method along the channels. As you can see, the gradient weights become noisy in layer 3 compared to layer 4. On the other hand, the relevance weights prove its robustness to the shader gradient problem, showing high selectivity in both layer 3 and layer 4. In D, all top 3 weighted activation maps localize a tangent well in layer 4. But in C, even the top 1 map selected by gradient CAM cannot localize the tangent well. On the other hand, Relevance-CAM is clearly localized the tangent, and the top 3 weighted activation maps also highlighting the target object. This indicates Relevance-CAM provides good weights for the important channels. Final test is class sensitivity test. As you can see in this figure, Relevance-CAM have high class sensitivity. And through Relevance-CAM, we can find that the Resonate 50 model already separates the elephant and the zebra from the layer 1. Thank you for listening.